Welcome to Math 360's Chapter 1, Section 4, Separable Equations, First Order Differential Equation Solutions method called Separable Equations and its applications. Well, what is a separable equation? Well, most differential equations start with this type of differential equation. And they are equal to some function that contains both the independent and dependent variables. Now, the differential equation is separable if this function that depends on the independent and dependent variables can be separated into two separate functions, one just of the independent variable and one just in the dependent variable. And then this can be separated into two ways. Here we have a multiplication, and the other one is a division. If this happens, then what we can do is we can move all the y variables to the left-hand side of the equation, and then we'll move the dx over to the right-hand side of the equation and integrate both sides. This allows us to be able to solve for y of x if we can do the integrations that are there. So we do this, well, let's start with this differential equation. To represent it in the form of a separable, I'll have to write it this way, and you can definitely see I have a separate function in x and a separate function in y. And so I'll move the y's over to this side and leave the dy with it and move the dx over to the right hand side and integrate both sides, and I have this these integrals to do. So you have integral on the left, integral on the right. Well, the one on the left is just log of y, and the one on the right would be minus x squared plus our constant c of our integration factor. Well, I should say, based it on integrating independent variables, you will get a constant c. So I still have to solve for the function y. So I have to take the exponential of both sides. In doing that, I come up with this definition of what y is. And we have minus x squared plus c in the exponent of e. And so, using the property of exponents, I can rewrite it this way, where I have this expression here of e to the c, but this is a constant. C is a constant, so e to the c is just another constant number. I have no idea what that constant is yet, so I'm going to just write it in terms of another constant called c1. Now, how do you find c1? Well, that's based on the initial conditions of the problem. I don't have any initial conditions for this problem, so what I need to do is so I just have this family of solutions that are left over in this case. Let's look at this example. Now here, this one has initial conditions. So this is definitely separable. I can move the y's over here and move the dx over there, end up and integrate both sides. And what I get is these integrals. So this integral again is just log of y, and this integral here is just e to the x plus a constant. So take the exponential on both sides, I have this. Apply our property of exponents, I get this. E to the c is a constant, so I'm going to just call it c1. Well, what is c1? Well, I apply my initial condition. At x equals 0, y has to be equal to 2 times e. So I plug that into my solution right here. I have e to the 0. Well, what is e to the 0? E to the 0 is 1. So I have e to the 1. So in order to make this valid, c1 has to be equal to 2. And so my solution is this for this differential equation. How about another example? So a lot of these separable differential equations have a lot of applications. One of them, this one, is a population problem, and you get this type of first order differential equation. This is very common. It also could be called radioactive decay problem, or exponential growth, or continuous interest, or elimination of a drug in a system. So this solution shows up, or this type of differential equation shows up quite a bit. Another one is called Newton's law of cooling. Another one is Torricelli's law. I've shown you them before, but they're all separable differential equations. So how do you solve this? Well, this is a derivative, so we have a change in our population divided by a change in time. So this problem states that we have a 6-fold change in the population in 10 hours, and that has to be equal to k times the initial population we had. So the population variables will cancel, and I get that my k is 6/10 or 3/5, however you want to write it. So I can plug that k back into here, separate my differential equations, bring the p's over here, bring the dt's over to the right, and I get these integrals. This integral is going to be the log of p. This is just going to be our constant 3/5 times t plus some constant. I need to find population p, so I need to take the exponential of both sides. Again, I want to get the constant out of the exponent, and I apply that by doing the applying properties of exponents. Now, what is C1? It is a constant. Well, what is that? Well, what I'm going to say is we have some initial population here. I'll call it P0 at t equals 0. So if you apply that initial condition, this is the solution that we would get for this system. And, well, how do I answer? How long does it take the population to double? Well, I've got to, at some time period, I need to get twice my population. This is what the solution should tell me. Now I can solve for t. My initial populations cancel, and I have this expression. Take the log of both sides, solve for t, and I get this answer. If I calculate t, I get the time it takes for the population to double to be 1.1553 hours. I'm sorry this podcast took so long, but that's what it is. We'll work some more separable differential equations in class tomorrow. Hope to see you there.